Chapter 1, Computed Tomography and Overview. This chapter explores the meaning of CT through a description of its fundamental principles and also the historical perspectives. We will also be discussing the growth of CT from its introduction in the 1970s to its transformation in today's technology, with an emphasis on the physical and the technical aspects of CT imaging. A conventional tomogram is the image of a section of a patient that is oriented parallel to the film. Transverse axial tomography is an image of a section of a patient that is oriented transversely to the film. This was developed by Watson in 1937, but these images lacked enough detail and clarity to be useful in diagnostic radiology. CT overcomes limitations in detail and clarity by using mathematics in the image reconstruction process from projections to produce sharp, clear images of cross-sectional anatomy. In CT, radiation passes through each cross-section in a specific way and is projected onto a detector that sends signals to a computer for processing. The computer then produces the sharp, clear images of the internal structure of the object being imaged from the information that it processes. In 1967, Hounsfield made the world's first clinically useful scanner. This was used for brain imaging, and his work, along with a combination of other developers, resulted in two types of CT systems. There's emission CT, which is a radiation source that is inside the patient, and there's transmission CT, which is a radiation source that is outside the patient. Hounsfield's work produced a technique that revolutionized medicine and diagnostic radiology, and he called the term computerized transverse axial scanning, which is what we know today as tomography. So the formation of CT images by a scanner involves three key steps. First, we will discuss data acquisition. This is the simple collection of X-ray measurements from the patient. This measures the attenuation values, so once the X-ray passes through the patient, the X-rays fall onto special electronic detectors that measure the transmission values, which are called attenuation values. This involves conversion of electronic signals, which are obtained from the electronic detectors, into digital data, in which the computer then uses to process the image. The next key step is image reconstruction. With image reconstruction algorithms are used. And after enough transmission measurements have been collected by the detectors, they are sent to the computer for processing. The computer then uses the special mathematical techniques to reconstruct the CT image in a number of steps, which are referred to as image reconstruction algorithms. So there are many different algorithms out there, and ones you may have heard of are back projection algorithms and interpolation algorithms. But iterative reconstruction algorithms are used today on all scanners, and we will discuss this more in Chapter 6 a little later. Image display, processing, storage, reconstruction, and communications are all included in the third step of the formation of CT images. After the computer has performed the image reconstruction process, the reconstructed image can now be displayed and recorded for viewing and also stored for later analysis. The image is usually displayed on a cathode ray tube, but today touchscreens are being used as well. However, the cathode ray tubes seem to be the best image display method for the display of grayscale imaging. Digital image processing is also known as image manipulation, and we'll discuss this more in depth in Chapter 2. Images can be modified through image post-processing to make them more useful to interpretation. An example of this is when transverse axial images can be reformatted into coronal and sagittal reconstructions. And other examples of image post-processing techniques include image smoothing, edge enhancement, and 3D image processing. So image recording has been done on film in the past, but laser cameras are now used. Image storage can be completed by using optical storage, although magnetic tapes and magnetic discs have been used in the past. With optical storage, the stored data are read by optical means such as laser beam. There are 3 formats of optical storage formats out there, which are disks, tapes, and cards, but we'll delve more into this in Chapter 7. In CT, communications refers to the electronic transmission of text data and images from the CT scanner to other devices such as laser printers, workstations, and display monitors. Communications today is done by DICOM standard with the use of PACS, and we will discuss this more in depth in Chapter 7 as well. So this slide is just an example of a step-by-step process of how a CT scanner works. So the X-ray tube and the detectors first rotate around the patient during the scan, and the tube and detectors are located inside the gantry of the scanner. Then the attenuation data is converted into analog signals. The detectors are responsible for this conversion into the analog signals. Then analog signals are converted into digital data for input into a computer, and the computer then performs the image reconstruction process. So now the reconstructed image is converted into electric signals to be viewed on a monitor. But the reconstructed image is in numerical form prior to the conversion into the electric signals. Then the images and data are sent to PACS for radiologist interpretation. And finally, the image is stored. And remember from the last slide that this is normally completed by using optical discs. All right, 2 important people right here on this slide. CT was made possible through the works of several individuals, but the main contributors were Godfrey Newbold Hounsfield and Alan McLeod Cormack. In 1967, Hounsfield found that if an X-ray beam was passed through an object from all directions and measurements were made of all the X-ray transmission, then information about the internal structures of the body could be found. In 1971, the first clinical prototype of the CT brain scanner was installed. And in 1972, the first patient was scanned. This patient was actually a woman with a suspected brain lesion, and the picture for this scan clearly showed a dark circular cyst on her brain. From here on out, it was obvious that CT was useful to distinguish the difference between normal and diseased tissue. For Cormack, he developed solutions to the mathematical problems in CT. He didn't gain notoriety until Hounsfield's work on the development of the first scanner. It was then seen from Hounsfield's work that Cormack's work was a solution to the mathematical problems and issues in CT. All right, so in 1974, the first whole body scanner was developed. And there were 3 generations of whole body scanners developed. In 1974, the 4th generation CT was developed. Take a look at figure 111 on page 9 of your textbook to see the 4 different generations of scanners. There's been a huge growth in image quality involving CT scanners over the years. This includes improved spatial resolution, decreased scan time, increased density resolution, and increased loadability, meaning the X-ray tube specification changes were made to accommodate more whole body scans. All right, in 1975, the first high-speed CT scanner, which was called the Dynamic Spatial Reconstructor, the DSR, was installed. The DSR performed dynamic volume scanning of cardiovascular and pulmonary systems with high temporal resolution. However, it is now discontinued. And then in the 1980s, another high-speed CT scanner was introduced, which was called the electron beam CT. And this was originally called the cardiovascular CT scanner. Siemens acquired the scanner and referred to it as the electron beam CT scanner, or the EBCT. This was invented to image the cardiovascular system without artifacts caused by motion of the heart. And the biggest difference between the EBCT and the conventional CT scanner is the absence of moving parts. So next we'll talk about spiral helical CT scanners, which is also called volume scanning. In conventional CT scanning, the patient is scanned one slice at a time, and the detectors rotate for 360 degrees or less to scan one slice while the table and the patient remain static. This was extremely time consuming, obviously, so the concept was made of scanning a volume of tissue by moving the patient continuously through the gantry of the scanner while the tube and detectors rotate continuously for several or multiple rotations, resulting in the X-ray beam tracing a path around the patient. The spiral helical CT scanners developed after 1989 were referred to as single slice spiral helical scanners or volume scanners. The dual slice spiral helical scanner was introduced in 1992, and this type of scanner scanned 2 slices per 360-degree rotation. This increased the volume coverage speed compared to a single slice volume CT scanner. Multi-slice CT scanners are based on the use of multi-detector technology to scan 4 or more slices per revolution of the X-ray tube and the detectors. And this was introduced in 1998. Check out figure 115 on page 11 in your book to see the increase in number of slices per revolution throughout the years. As of 2007, there was a 320 slice CT scanner on the market. This means that there are 320 slices per X-ray tube revolution. So one of the main goals in the development of the CT scanner was to achieve isotropic resolution. This is where the voxel is a perfect cube, so equal length, equal height, and equal width. It improves the image quality by making the 3D images sharper in appearance and not exhibiting the stair-step artifacts that are seen in non-isotropic resolution 3D images. Moving on through the development of CT scanners throughout the years, there was a dual source CT scanner introduced in 2005 at RSNA by Siemens Medical Solutions. This scanner was called the Somatome Definition, and it is also known as the Dual Energy CT. We'll be talking about this quite a bit throughout the remainder of the course. This type of CT has 2 X-ray tubes that operate at different energies. So it features 2 tubes and 2 detectors. And it is specifically used for imaging cardiac patients in short time frames. And the biggest benefit of a dual source CT scanner is that it has high temporal resolution. So there are other technical applications of volume CT scanners that are used, and we will discuss some of these a little bit more in depth throughout the remainder of the course. But they include CT fluoroscopy, CT angiography, 3D imaging, virtual reality imaging, improved cardiac CT imaging, radiation therapy, and also in nuclear med, a CT scanner is combined with a PET scanner, and this is called a PET CT scanner. And there is also a single photon emission photography scanner to form a SPECT CT scanner. There is also even a portable CT scanner on the market. It is being used clinically, which was first introduced by Philips Medical Systems. The portable CT scanners are used to image patients who are too ill or physically traumatized to be transported to a regular fixed CT scanner. This was first introduced specifically for use in the OR, ICU, and the ER. So I'm sure you've noticed that radiation dose has been a topic at the forefront of this imaging modality for the past few years. Several imaging parameters affect radiation dose in CT imaging. These include slice thickness, noise, resolution detector efficiency, reconstruction algorithms, collimation, and filtration. Dosimeters measure dose in CT, and there are a few different dose descriptors that are used in CT, and these include single scan dose profile, multi-scan dose profile, CT dose index, multi-scan average dose, and isodose curves. We will discuss some of these dose descriptors a little bit more in Chapter 10. So one scheme to keep the patient dose to a minimum during data acquisition includes 3 parts. The first is combined applications to reduce exposure, and this is where a pre-patient filtering technique is applied, and it reduces the dose by 15%. The second part is the use of new ultrafast ceramic detectors, and these detectors actually reduce the dose by 25% in a CT scan. The third part is online dose modulation. This is also known as automatic tube current modulation technique, and this is where the MA is optimized to the patient characteristics in order to reduce the dose. I want to take some time to discuss a few technology trends that are occurring in CT today. Some of the major trends include iterative reconstruction algorithms, CT detector technologies, dose reduction, spectral CT imaging, graphics processing unit computing, and faster imaging techniques. And while we will discuss some of them now, we will also touch on some of them in later chapters. With iterative reconstruction algorithms, they were initially created in the beginning of the CT scanner birth era, but now this topic seems to be resurfacing a lot in the current field. Since 2014, all major CT manufacturers actually offer the iterative reconstruction algorithms. These are used in order to overcome the problems brought on by filtered back projection, which was being used, such as image noise and streak artifacts on images. The goal with the IR algorithms is to reduce image noise and reduce the higher radiation dose, which is seen in the filtered back projection. And don't worry, we'll get into this a little bit more later as well. Remember, this chapter is just an overview. There are two categories of detectors. There is the solid state or the scintillation detectors, and these have evolved from sodium iodide detectors that were used early on in the inception of CT, and they consist of scintillators coupled to photodiodes. Scintillators that are used by recent high-end scanners include gadolinium oxysulfide, ceramic, gemstone, and ultrafast ceramic. Another type of detector is the gas ionization, or the xenon gas, and these have become obsolete. Another major technology trend is radiation dose optimization. So with this trend, it advocates for the ALARA principle when considering dose reduction. It balances dose reduction without the loss of image quality, or it tries to. The requirements for dose image quality optimization research include ensuring patient safety, determining the level of image quality required, obtaining the images at various exposure levels, ranging from high to low, and using reliable and valid methodologies for dosimetry, image acquisition, and the evaluation of image quality using human observers. Another trend is the spectral CT imaging, or the dual energy CT. This confronts how to utilize broad energy spectrums from the X-ray tube, reaching the detector. CT scanner product data is usually obtained from the manufacturers and is especially important when considering the purchase of a new scanner. The important features of the scanner could include application, features, composition, the sighting requirements, outline drawings, and the performance specifications. Under the performance specifications, this could include the X-ray generation, like the tube and the generator, X-ray detection, data processing, data storage, image display, image processing, system and dose management, and clinical applications, and the data transfer. Some more areas of the scanner product data include image quality, and what falls under image quality includes noise, spatial resolution, high contrast resolution, and high and low contrast detectability. System components and their functions, operating features, which could include patient handling or positioning, the scanning, data processing, image display and processing, and patient throughput. Compliance and dimensions and mass are two more areas of scanner product data.